Alright, so last time we talked about experimental probabilities and we talked about theoretical probabilities. And we talked about how an experimental probability is kind of calculated through an experiment. So we look at whatever a favorable event is. Say we want to know the probability of heads. If we flip a coin, then we'll flip it some amount of trials, say 10, and over that we're going to put the number of actual heads that we get as results. So say out of 10 trials we only got 3 heads, we would put 3 over 10 and say that our probability of heads, empirically or experimentally, is 30%. Now, the theoretical probability is your number of favorable outcomes divided by your total number of outcomes in your sample space S. Right, so our sample space in this case is either just heads or tails. Heads is 1 out of 2 outcomes. So in this case, our theoretical probability would be 50%. Okay, so this is where we ended last time. So today we're going to dive into more ways of calculating theoretical probabilities in more complicated scenarios. Okay, so let's start with this example here. Suppose you and your friend are playing a game involving rolling a die. So this is your fair 6-sided die. If the number comes up as even, you win. If the number comes up as odd, your friend wins. So what's the probability that you both win on a single turn? Okay, so you're going to think about this problem the same way we start off, or have started off, all theoretical probability problems. We start with our sample space. So this is just all of the possible outcomes we can have. The values 1 through 6. Okay, now let's say you're player A. If the number comes up as even, you win. So A, your winning possibilities are 2, 4, and 6. For your friend, who's player B, the winning possibilities are odd numbers, so 1, 3, and 5. Now, to calculate the probability that we would both win, we have to consider the intersection, right? The intersection of these lists. What number, if any, appears on both lists? That's the question we're asking ourselves. So, over here, we have a little bit of a Venn diagram. You can kind of list your possibilities here. So for A, you have 2, 4, and 6. For B, you have 1, 3, and 5. And then what we have in the center is what we call A intersection B. So it's written with this little N-looking symbol, A intersection B. It just means A and B. And in this case, there is no intersection between odd numbers and even numbers. So this intersection, it's empty. Okay, so space is empty. So on this list over here, I'm not going to put anything within that list. There's nothing that fulfills the criteria of being on both lists at the same time. Okay, so if I have to calculate the probability then of A intersection B, or A and B, it's the same idea. I would have written on top the number of elements within this list, but as we can see, clearly it's empty. Okay, so it's 0 on top, and it's divided by the total number of elements in your sample space, which are 6. So this is 0 over 6, which is 0. Okay, so in this case, these events have nothing in common. And these kinds of events are known as mutually exclusive events. Okay, that is, they don't intersect. They have nothing in common. They are mutually exclusive. Okay? But that doesn't have to always be the case. Let's see another example here. So now suppose the game is modified so that you win a point if any of the multiples of 3 come up on the die, and your friend wins a point if an even number comes up. Now what's the probability that you and your friend both win a point in a single turn? So first, let's consider your winning values. So multiples of 3 would be 3, 6, 9, so on and so forth. On a die, only 3 and 6 meet this criteria. And for your friend, the same values hold, so it's 2, 4, and 6. Okay? So if I were to write this, well, I'd write 3 here, I'd write 2 and 4 here, and in the middle, I would write 6, because now 6 is a value that shows up on both lists. Okay? So in my A intersection B, or A and B list here, I'm just going to put a 6. 6 is the element that both A and B have in common. It's the outcome. It's their common outcome. Okay, well now I use the same formula. So the number of elements on my A and B list, which is 1, divided by the total number of elements in my sample space, which is 6. So my probability in this case of both players winning is 1 out of 6. There's one number that, if rolled, will give us both a point. Okay? And that number is 6. So this is the common element, or outcome. Alright, so just to review really quickly, mutually exclusive events are those where two events have nothing in common. So A and B are mutually exclusive whenever A and B is equal to 0. For the second case, we call these simply overlapping events. They have some common element, or overlap. So that's the sort of opposite of mutually exclusive. Alright, let's look at example 3. Suppose we want to calculate the probability that one event or another event might happen. Okay, so in the last example, we just calculated the probability of A and B winning. Right, now let's consider the probability that A or B might win. So in the last example, you win a point if the die comes up as a multiple of 3. Your friend wins a point if it comes up as an even number. What's the probability that either you or your friend wins a point? So here we have the event space of A's winnings. If 3 or 6 show up, player A wins. And if 2, 4, or 6 show up, B wins. Now, for A or B, this is going to be each outcome that appears in either A or B, but written only once at maximum. This is because we don't want to double count the overlapping outcomes. Okay? So from one list, I have 2. From another, I have 3. I have 4, and then I have 6. Okay? So 6 appears on both lists, but I'm only going to write it once. That's our overlapping event or outcome. I don't want to write that twice. Okay, I don't want to double count that. So in this case, there are 4 possible outcomes which would allow either A or B to win out of 6 total outcomes. Okay, so 4 out of 6, this reduces to 2 out of 3. So that's my probability that either you or your friend is going to win a point. All right, but this follows, so we did this kind of looking at the event space and sample space, but it follows actually a general formula. So the probability of A or B, so this symbol, which is like, looks like a U, it's also known as union. So the other one was known as intersection or and. This is union, which we read as or. So this is equal to the probability of A plus the probability of B minus the probability of A and B. So what we're doing here is we're subtracting the probability of obtaining their common outcomes to prevent double counting, just like we saw before, right? So probability of A, let's see this in action. We have 2 events out of 6. Probability of B, we have 3 possible winning events out of 6. And then we have to subtract that one common event that they both share, which is the 6. So if you do it this way, 2 sixths plus 3 sixths is 5 sixths minus 1 sixth is 4 sixths, or 2/3 again. Okay, so this is the more formulaic way to calculate the same probability. If the events are mutually exclusive, then as we know from before, the probability of A and B is equal to 0. That means if we're trying to calculate the probability of A or B for mutually exclusive events, this is just going to be probability of A plus probability of B. There's nothing to subtract off because they don't share anything in common. So there's not like, just like how there was the 6 here that we had to not double count because it appears here and it appears here as well. We want to subtract off one of those. We don't have to do that for mutually exclusive events. Okay, so that's a simple case of you just add each probability together. All right. So now let's try to find, so for example 4, let's try to find the probability that the die shows an even number or an odd number. So the probability of even or odd, according to the formula, is going to just be the probability of even plus the probability of odd minus the probability of an even and odd number occurring. So there's 3 out of 6 even numbers. 3 out of 6 of those numbers are odd. There's not any number by definition which is even and odd. So that's 0 out of 6, right? So this is another case of a mutually exclusive event. So we didn't really need to include this part here. And regardless, we get 6 out of 6 or 1. So the probability is essentially 100% that we're going to land on either an odd number or an even number. All right. Now let's consider what are called complementary events. So what if we're interested in finding the probability of something not happening? Okay, the event that E does not occur is known as E complement. So this E with the little C on top as a superscript, this is read as E complement. This is the event that E does not happen. The probability of E complement is equal to 1 minus the probability of E. So the way you can read this is the probability that E does not occur is equal to 1 minus the probability that E does occur. Okay, so let's try an example with this. What's the probability that it doesn't rain tomorrow? Suppose the weather is showing a 40% chance of showers tomorrow. Okay, so probability of no rain is going to be equal to 1 minus the probability of it raining. And we know that the probability of it raining is 40%. So we're going to do 1 minus 0.40, and you get 0.60, or 60%. As simple as that. So this is sort of a diagram of E and its complement. So this entire box is your sort of sample space, your complete sample space. This is every possibility you can possibly have. And then E represents all of your favorable events or your favorable outcomes. E complement naturally is going to be everything outside of that. So it's the opposite of it. So taken together, E and E complement exhaust the entire realm of possibilities, which in this case is the sample space S. In other words, the probability of E complement plus the probability of E have to add up to 1, right? So it's a 100% chance that either E happens or it doesn't happen. And that's exactly where our top formula up here is coming from. So it's just a rearranging of that formula. All right, so let's look at our next example. Example 6 says, suppose that 14% of Americans can speak Spanish, 2% can speak French, and 1% can speak both. What percentage of Americans can speak neither Spanish nor French? Okay, so this is a problem that's going to sort of synthesize the formulas we've just learned. So first, we're going to start off by finding the percentage of Americans who speak either Spanish or French. Once we can do that, right, so that's like our E, we can find E complement, the percentage of Americans who speak neither. Okay, so let's define our events here. We've got S. This is the event that a randomly selected American speaks Spanish. We've got F, the event that a randomly selected American speaks French. Okay? So from here, the probability that a randomly selected person speaks Spanish or French, according to our OR formula, is going to be P of S plus P of F minus the probability of both S and F. Okay? So we know 14% of people speak Spanish. We know 2% of people speak French. And we know 1% of people speak both. 1% of Americans. So once we do this math, it comes out to 0.15, approximately 15%. All right? So 15% of Americans speak either Spanish or French. From here, since we know 15% speak either Spanish or French, using the complement formula, we can figure out what percent speaks neither language. So the probability that they speak neither Spanish nor French is equal to 1 minus the probability that they speak Spanish or French. So you have 1 minus 0.15, which is simply 0.85. Okay? So according to this, roughly 85% of Americans speak neither Spanish nor French. And these are just estimates of the real values. All right, now let's look at one last example. So, we've got this table here of 665 people. Suppose we're going to select one person at random from this table. So this table is showing people organized by both education level and marital status. So marital status is this way, education level is this way. You've got less than high school education, only a high school education, or a college education. And you've got single people, married people, divorced, and widowed. And then out here we have the totals for each. So this is total of single, total of married, total divorced. This is going to be the total of all of your education statuses. So this is the total number of people who went to college, total number of people with only a high school education, total number of people with less than a high school education. And in both directions, if you were to add this way or this way, it should add up to 665, which is our total number of people. So naturally, because we have people in every cell, every person meets or has some sort of education status, and they have some sort of marital status. So there's people who are both single and have less than a high school education, for example. All right. So this is the basics of it. It's called a two-way table. Okay, so first off, what's the probability that a person is married? Well, we've got our married column here. The total number of married people is 408. So the probability that a person is married is simply 408 out of the total number of people, 665. Okay. Now, what's the probability that a person has, that the randomly selected person has a college education? Okay, so the probability that person has a college education, well, you're going to go to the college row. We're going to find the total value here, which is 143, and divide that by 665. And that's our probability, that a randomly selected person has at least a college education. Now, we're going to consider what's the probability that the person is married or has a college education. Well, this is going to meet our probability of A or B formula. And that's going to be equal to the probability that they're married plus the probability that they have a college education minus the probability that they meet both criteria, that they are married and have a college education. Okay, well, we already have these first two numbers. So this was 408 out of 665. This was 143 out of 665. And now we need to subtract from this their overlap. So if we come back over here, when we were counting the married people, we went down this way. So we counted the 70, 240, and 98. When we were counting the people with a college education, we counted this way, horizontally. So we counted this 27, the 98, 15, and 3. So when you write it like this, what you see is that we've actually double counted this 98. So this 98 are those people who have both a college education and are married. And that's the group. So because we double counted that group, we're going to subtract off one of those values, or one of those 98s. Right? And this is going to give us our final answer, which is 453 out of 665. And that's it. That's the concept in practice.